All right, everybody, let's get the lecture going for this afternoon. Very good to see everyone here. Is the weather still pretty dismal outside? It was, yeah, okay. Well done, everyone, for making it in through there. At least we won't have to worry about that for the time being. So this week, what we're going to be thinking about comes under the subject of elastic materials. Now, you might think when I say elastic, is this all going to be about elastic bands? Maybe that seems a kind of specific thing to be thinking about. But remember last week when we were looking at stress and strain, and we had that what we call elastic region. So that region of materials where they're in that elastic region, so you can bend them a little bit and then they go back to their original shape. That gives rise to an absolutely extraordinary array of physical properties. So in a couple of weeks, we're going to be focusing on waves, and all of the physics that we get from waves are due to elastic properties of materials. So whether you're thinking about, like a stick or a slinky, or even things which we don't normally think of as elastic, like a table or a chair or something like that. They all have elastic properties, and it's understanding these properties which is absolutely essential to understanding those aspects of the physical world. So it's a really important, really exciting area of physics. So that's the plan for what we're going to be thinking about for today. Now, I always like to start with a picture, something that's got some connection to what we're going to be thinking about. Now, today, I didn't have a picture which is exactly called elastic physics. In fact, it's a pretty good example of inelastic physics, but I just thought it was such an extraordinarily exciting picture. I thought it would be an interesting one to start with. So has anybody seen, if you're following along, this amazing picture from the Artemis I mission? So this is a picture taken from the solar panel of the Orion spacecraft this afternoon as it's orbiting the moon. And this circle that you can see over here, so that's planet Earth. And in order to get this far, and certainly if you want to get back, you've got to use all of the physics concepts that we've been learning about all semester. Now, something I'd like to say about the physics that we're going to be learning, certainly today and throughout the rest of the semester, is that previously, we've been focusing on a slightly different topic each week. So maybe one week it's kinematics, next week it's energy, that kind of thing. But of course, physics, it's not really divided neatly into chapters that are kind of convenient each week. So even though this week we're learning about elastic physics, what I'd like to really start doing today and for the rest of the semester is to start linking the new concepts that we're learning into some of the previous concepts that we've already seen, and really making those connections and seeing how they apply. So today, when we're learning about elastic physics, I'd like to see how that links in to some things that we've learned previously about Newton's laws of motion. So we're going to do a bit of a recap, bit about Newton's laws of motion, and see how we can actually understand them and apply them a bit better once we understand a bit of the elastic physics involved. Before we get to that, something I was thinking about with this picture is that this Artemis I mission, it's in a sense a full dress rehearsal of what a human-rated mission to the moon could look like. So in principle, you could put someone in this space capsule, and so far they would have had a pretty nice ride all the way out to the moon. And if you looked out the window, that's what you would have seen. And this got me wondering, because I thought, well, suppose there was a space available in the capsule. Would you really want to take that? Would you want to take the risk of taking this voyage out to the moon, or maybe you'd want to wait for one of the other missions? So I just thought, to get the lecture started today, I'd like to get everyone's opinion on this. So suppose the Space Launch System rocket was about to take off, and they said, hey, do you know what? We've got a spare seat. Would you like to take a ride on this if it was available? So I'd like to hear from all of you guys. If that was available, would you like to go on it? Or if you might say, well, okay, this is the very first test mission, maybe I'll wait for a later mission, maybe you want to stay on the ground at all. I'm actually really curious to see what everybody thinks for this. So I'll get the question going. Let's take a look at the results in just a moment. So if you guys aren't sure, maybe you want to bounce some ideas off other people around you, that's definitely a good idea. It's obviously a big decision here. Okay, let's take a look at the responses. I really am curious to see how adventurous everybody is here. Let's take a look. Okay, wow, great. So 14% of you would be up for going on this very first test mission, the very first launch of this rocket. I'm impressed there. Who's some of the people who would be up for going on the first launch? Okay, wow. So you'd be up for giving it a go?
Yeah.
Yeah?
Worst case scenario, you die, but at least you die in a cool, unique way.
Okay, worst case scenario, you die. Yeah, fine.
Best case
Yeah, but it's going to be pretty cool.
Yeah.
What would you like about it? Like seeing the Earth from space, or just traveling out to the moon?
Yeah.
Awesome. I think that's great. Why not? Who else would be up for giving this a go on yeah. Why not? Awesome, fantastic. And anybody else who would be up for this? If they said, look, totally first time we've lit this rocket, but if you want to go, who else would be up for it? You'd be up for it? Are you being peer pressured into this? Okay, you go together. Okay. Well, I think that's great. Okay, now who wouldn't want to go on any of them, even if, okay, why not? Just not so keen, or?
I think my dad would get mad at me.
Okay, yeah, I think that's a good point. I think, and someone else not so keen at the back there? Okay, so that was after the Challenger disaster, not taking any chances. And I think that's a good point, because the Challenger disaster, it was all due to the solid rocket boosters and the O-rings. And actually, they have kind of basically the same solid rocket boosters with the Space Launch System. So I think that's a fair point. Anybody else who wouldn't want to go, even if they said, look, free ticket, spend the next, who you wouldn't be so keen? Why not? Just safety, or just, you might die? Yeah, I think that's a legit reason. I think some people think it'd be cool, worthwhile. Okay, now, what I'm really interested in are these people in the middle here. So some people you would be up for going, but you wouldn't want to be on the first trip. Who's in that situation? Okay, and is that just because you want to see it's all worked first? And yeah, I think that's reasonable. I think I might say, well, let's see this first one come back safely. And what would I? I think I would be more in the this one. I think I'd say let's see them do the first one. Once it's landed and parachuted and everything, then maybe we'll think about it. Yeah. Now, who would be up for this one? Like, it's not worth going unless you're going to land. Who's in that situation? Yeah.
I want to go play golf on the moon.
Play golf on the moon. Fantastic. That's brilliant. Obviously, you can't do that from orbit. Anyone else who would want to go, but only if you're going to land? Anybody else? Okay, well, I think that's a great range of responses. I have to say, I'm quite impressed how many people would be up for going on the very first one. That is quite adventurous. So before we move on to a bit more the elastic physics, I've just got one more thing that I'd like to share with you, because I think when we're thinking about whichever one of these, obviously it's great you can play golf on the moon. That would be quite exciting. But I think a big reason, certainly why I think would be exciting, is because of just the extraordinary views, right? And to look back and see Earth from space, I think that would really be extraordinary. And certainly when it comes to astrophysics as a whole, the kind of visual appeal of it, certainly for me, it's always been something which has been very appealing, all of these amazing things you can see in space. And this actually brings me on to the physics seminar that we're having this Wednesday. Now, has anybody heard of the physics seminars that we have in the department? Has anybody told anyone about this? Okay, so every Wednesday, alternating, there's physics and chemistry seminars. So Wednesday afternoons at 1 p.m. And everybody is very welcome. They're kind of aimed maybe a bit more at kind of final year students or PhD students, but everybody's welcome if you see something that you're interested in and you'd like to find out about. Now, this week, we have a really fantastic speaker and a really brilliant talk, and I think it would be really of interest to everybody. So I'd just like to share with you the details about that, how I think if you might want to come along to this. So the talk, it is this Wednesday, Lecture Theatre 3 at 1 p.m. Do you guys know where Lecture Theatre 3 is? The big bit by the library. So that's where they are. So this week, we've got a great speaker coming from the University of Portsmouth. We've got Dr. Nick Bond, and he's telling us about a really fantastic project to make astronomy and astrophysics more accessible to the visually impaired community. And I think this is such a great project, and there's so many really fascinating angles to this. So Dr. Bond, he is himself a astrophysicist, but he also has a visual impairment. So one of the things he was thinking about is how to make astronomy accessible to students who have visual impairments. And the project that he's been working on and leading, it's this fantastic project called the Tactile Universe. And this project is all about 3D printing astrophysical images and developing teaching resources to make astrophysics accessible to people with visual impairments. So I think it's an absolutely fantastic project. I'm really looking forward to the talk. And there's lots of different angles why you might be interested in this talk. So it's been great to chat to some of you guys in the workshop. I know some of you are interested in astrophysics. So Nick's astrophysics background, it's in the field of galaxy evolution. So if you're interested in galaxies or astrophysics, maybe you might want to come along, hear some of that side of things. Also, I know some of you maybe you're interested in going into teaching, science communication, accessibility, that kind of thing. So if you'd like to hear about how they've built this project up and really made this fantastic accessible program, that's another angle that you might be interested in. I'd really encourage everyone, come along to this. I think it's going to be a fantastic talk. Now, let's move on to the main physics topics of today, thinking about elastic materials. So we saw this slide at the end of the last lecture when we were looking at stress and strain. So the whole situation there is we have some kind of physical object and we're applying some force, exerting some stress along the object, and that causes the strain, so the change in length. And we just saw at the end of the last lecture that if we look at the ratio of the stress and the strain, we can define what we call the Young's modulus. And the Young's modulus, it's a property of the particular material. So some materials are stiffer than others, or if you have a slinky, it's very stretchy, stretching all over the place. And that stiffness, that property, is described in the Young's modulus. And by thinking about the Young's modulus, we can actually understand a lot of physical phenomena, some that we're going to see very soon, and some that we've already seen we can understand in some more detail. So let's start with a bit of a question thinking about Young's modulus, because we know how it's defined in terms of stress and strain. So let's start with a bit of algebra and think, how can we relate Young's modulus to the things that we're applying to our object? So the force and the change in length. So a bit of algebra to get things going with this question. Let's see what everybody gets for this one. I'll get the question going. So with this one, you don't have to guess with this one. We're just working through a bit of algebra with this one. Okay, let's see how everybody did for this one. Let's take a look at what we've got here. So when you do the substitution. Okay, so looks like not so many people going for B and D, but most people are going for A and C. So maybe it might just be useful to put a little bit of the algebra up on here. So we've got that our Young's modulus is equal to our stress divided by our strain, and the stress is force per area, and the strain, it's our change in length divided by our original length. So these are the pieces of the puzzle. So if we start by thinking, well, what is our Young's modulus going to be? So our Young's modulus, so it's going to be the stress, so the force per area, and then we're dividing by the strain. Now, dividing by the strain same as multiplying by the reciprocal. So it's the same as multiplying by L naught over delta L. So what do we get there? So force times L naught divided by A times delta L. So that's option A up there. So looks like very well done everybody who got option A, but especially if you gave the question a go, okay, because the important thing is to engage with the algebra. Now I would emphasize, if you look at a question like this and you think, oh, it's just a bit of algebra, I'm fine with algebra, don't really need to do this, I'll just see what we get. Make sure you give it a go, because quite often when you actually get down to it, it can be a little trickier than you might have first thought, and you just want to make sure you're really practiced and really familiar with the algebra there. So very well done everybody who gave this question a go. Now you don't need to memorize this equation, but it is a useful expression to have, because what this allows us to do is it allows us to relate things that we might do in an experiment. So, we might be thinking about how much force we're exerting, and we might be measuring, what the delta L is. And that allows us to link these two to the physical properties of the materials. So if we think about a material, if we think about this stick, you can measure how long the stick is, you can measure how much force you exert on the stick, you can measure how much the stick changes, but you can't directly read off what the Young's modulus of the stick is. It's not written on the stick anywhere. The only way you can figure it out is by doing an experiment and working through the math. And it's an important thing to do, because once you know what the Young's modulus of the material is, you know the physical properties. So if you want to be building something out of it, that's what you need to know to understand how the material is going to behave. Another great thing about this expression is it actually allows us to understand one of the things that we scratched the surface with when we were dealing with Newton's laws. We can now understand in more detail. So I'd like to take one slide to recap something from Newton's laws, see how much people can recall from that. And then we'll see how we can understand that a bit better when we think about the Young's modulus. So let's take a look at this question here. This is the exact same question from a few weeks ago that we had with Newton's laws of motion. So we had this situation where we put something on a surface and the thing has got a force of gravity, and we get that there's this equal and opposite, what we call normal force. So what I'd like to think about here is, why is the normal force equal and opposite to the force of gravity? So we might have to recall a few things from a few lectures back, thinking about Newton's laws of motion, but it's always good to be making those connections between different physical concepts. We don't want our physical ideas to be siloed and kept separate. It's really good if we can start making the connections between these different concepts. All right, let's see what everybody thinks for this one with this Newton's laws of motion. Okay, so we've got some people going for all of the options there. Looks like most people are going for option B. Now, maybe let's start with option C. So we do know that if we have something on a surface and it's at rest, we do know that the resultant force must be zero. But in a sense, that's a bit of a kind of circular reasoning. What we're really thinking about here is, why are those two forces equal and opposite? So it is correct that we know that the net force has to be zero, but that doesn't help us to explain why the normal force is equal and opposite to the force of gravity. Now I can see why people might be going for option D, because Newton's law, third law of motion, it does tell us every force has an equal and opposite reaction force. So if there's a force of gravity of an object, then there's got to be an equal and opposite reaction force. And you might also be thinking, maybe you've heard somewhere that they form a action-reaction pair. But remember that if we have an object and there's some force of gravity acting on the object, the reaction force to that is the force of the object's gravity on the Earth. That's what the action-reaction pair is. So as looks like most people have got, which I'm really pleased about, the reason that these forces are equal and opposite is because when we have a surface, they get compressed, and that compression keeps on going until it's equal and opposite to the force of gravity. So very well done, everybody who got that question. I'm really pleased to see so many people getting that question right, because this is a very common misconception when we're thinking about Newton's laws of motion. One of the reasons why it's such a common misconception is because if we think about a surface like this desk, we really can't see anything compressing very much. If we have something very stretchy, like a slinky, and we stretch it out, you can really see the stretching going on. But most kind of everyday things, it doesn't look like things are compressing. It looks like things are, pretty substantial, and they don't move when we apply forces to them. But the great thing about Young's modulus is, now that we know how to relate forces and lengths, we can actually work out what this compression needs to be. And it's a really interesting example, and it actually helps us to understand this situation with Newton's laws of motion. So let's take a look at this situation here. What I'd like to think about is essentially the physics of sitting in a chair. Now, oh yeah, that's the correct answer there. We've got option B. So what we're thinking about here is the physics of someone sitting in a chair. Now, we just had our open day on Saturday, and we had loads of students all very excited about coming to university learning physics. Quite often they're saying, they want to learn about particle physics and astrophysics and quantum mechanics, and they've got all that great stuff to look forward to. And in fairness, I don't think we had anyone saying that they wanted to learn about the physics of sitting in a chair. But it is a really interesting thing to look at, and there's actually some quite surprises, and you might never quite see the world the same way once we've worked through the physics of sitting in a chair. And once we work through this, certainly in the next semester, we've got all that good stuff to look forward to. We're going to be doing all the quantum physics, all the electromagnetism, orbits, all of that good stuff. So for now, let's think about this situation where we have someone sitting in a chair. Now, from this equation with Young's modulus, we're going to need to know the force. So let's start with this question here, where we're figuring out the force on the chair due to someone sitting in it. So with this question, there's lots of information here. We are going to need all of this information eventually. But for now, we're just thinking about the force due to the person sitting on the chair. So we don't need all of this information. So have a look there. What's going to be the important thing we need to figure out the force of someone sitting on the chair? Okay, very good with that one. Good to see the responses coming in. Let's see what everybody thinks for the force of the person sitting in the chair. Let's see what we get here. Okay. So it looks like most people going for B. Okay. Now, with this one, it might be a bit tricky because we have quite a lot of numbers up there, but we don't need all of them to work out the force. So with the force, it's just the force of gravity due to the person sitting in the chair. Force of gravity, it's just mass times the acceleration due to gravity. So it's just, our force of gravity, it's just equal to our mass times that little g there, the acceleration due to gravity, so the 9.8 meters per second squared. So when you do that, when you work out the force, we get option B there. So very well done to everybody who gave that question a go. Correct option is option B. So we know the force acting on the chair due to the person. So that's a big piece of the puzzle that we need to figure out. Now we know the length of the chair, how long the chair legs are. You can just measure that with a ruler. That's pretty straightforward. The next big piece of the puzzle that we need to relate everything in Young's modulus is what this area is. And remember, when we think about stress and strain, the area is what we call the cross-sectional area. So the area that's actually providing the support to that force. So in this case, it's coming from the legs of the chair. So with this question, bit of geometry involved, a little bit of algebra involved. We've got to work out, based on what we can measure for the legs of the chair, what is that area? It's not a surface area, it's a cross-sectional area. That's the area which is supporting us. So let's give this question a go. let's see what everybody gets for this one. So again, with this question, we don't need all of the numbers which are provided in the question to work out the area. There's just a few values that we need there. So it's quite important to be able to pick out the parts of the question that are going to be important. See what you get there. What do we get for that cross-sectional area of the legs of the chair? Let's see what everybody gets for this one. What's the cross-sectional area of our chair? Okay, nobody's going for C. Looks like quite a lot of people going for D. Not so many people going for A and B. So what we got to do, we need to work out the area of one of the legs and then multiply it by 4. Now with the area, because they're all in meters squared here, did anybody convert the distances to meters before working out the area? Did anybody do that first? Okay, and who works out the area in like centimeters squared and then converted it? Okay, few people did that. So it's up to you which way you want to go. Just be a bit careful if you're converting from centimeters squared to meters squared. Personally, I prefer to convert centimeters to meters first and then work out the area. But however you do it, it's up to you. So when you work out the area, so the area of one leg and you multiply it by 4, what we get, option D here. So the 5.81 times 10 to the minus 3 meters squared. Now you might say that's a very small area, that 10 to the minus 3. That comes really from converting the centimeters squared in the meters squared. So very well done everybody with that question, okay. Now we're ready for the last piece of the puzzle, thinking about Young's modulus here, because we have our cross-sectional area, we have our force, and we have our length. So what we can do is we can work out how much the chair is going to be compressed due to the force of someone sitting in it. So let's try with this last question here. Based on all of these things that we've worked out, so we know the force, we know the area, and we also know for wood that the Young's modulus is about 8.8 gigapascals. Now that might sound very high. That's really telling us it's not very compressible like that, okay? So let's see what everybody gets. How much is our chair going to compress due to the force of someone sitting in it? So what I would suggest with this one is do the rearranging, do the algebra first. So solve for the delta L first before substituting any numbers in, then substitute in the numbers and see what you get. That's going to make life a bit easier for you. Okay, let's take a look at the responses. Let's see what everybody gets for this one, okay? All right, okay, so nobody's going for D. Some people going for A, some people going for C. Looks like most people going for D. Did anybody rearrange the equation first, do the algebra before putting the numbers in? Who solved it that way? Everybody else, just a few people, otherwise you sort of put the numbers in and figure it out. So it does make it easy. If you start from this equation, just solve for the delta L first before putting any numbers in, makes it a bit more straightforward when it comes time to put the numbers in. And when you put the numbers in, when you do the math, what we get, it's that 5.6 microns. That's how much our chair is going to be compressing. Now, the important point I want to make about this is really a big deal for explaining what's going on with Newton's third law of motion and this reaction force. Because you might say, well, okay, if I'm, supporting my weight through this desk, it doesn't look like the desk is compressing at all, but the net force on me is 0. It just looks like there's almost magically an equal and opposite reaction force, and maybe that's due to Newton's third law of motion. But now that we understand Young's law, some of the elastic physics involved here, we can actually work out how much things need to compress in order to provide an equal and opposite force. So we can see with a chair, it's just compressing a few microns, so a tiny, tiny amount. You'd never be able to see something like that. That's all you need to compress a chair in order to provide an equal and opposite force and to stop you falling through the ground. And that's one of the reasons why it's very easy to miss. So when we're talking about elastic physics, you might not instinctively think to things like, chairs and tables, but remember that at a certain level, everything's kind of stretchy and made of slinkies. Everything has a degree of elasticity in it. And in the next lectures, we're going to be finding a lot more about that. And it's extraordinary, the whole kind of world of physical phenomena it opens up. Now, I just have one more slide, last slide, just a few announcements before we wrap things up for today. Let's take a look here. Now, I do have 3 quite important announcements here. Here we go. Okay, so last slide for today. I know it's last thing on a Monday afternoon, but I do just have 3 quite important announcements, and then we'll wrap things up for today. Okay, so announcement number 1. So just a reminder, the coursework is due. Now, it's due on the 2nd of December, and I know that sounds like a very long way away. You know, December, I can't believe we're even talking about December, but remember, that's only the Friday after next. Okay, so you got this Friday, and then the Friday after, that's when the coursework's due. So you can submit it on Blackboard. It's got to be in by 3 p.m. Otherwise, Blackboard, it says, oh, it's late, and there's just nothing we can do about it. So give yourself plenty of time. There's still plenty of time now. It was great to see some people at the workshop last Friday already getting started with the data. Okay, so there's plenty of time for the coursework. Just don't leave it too late. If you're wondering where the material is, all the material you need for the coursework, it's available on Blackboard under week 7. So all the data and all the description of the coursework, that's where that all is, okay? So the second important announcement, okay, so you may have heard that there's not going to be any lectures later in this week, because has anyone told you guys about this, or what's going on with this? You've been sent emails, okay. So I'm not sure exactly what you've been told, but so we're not going to have the lecture or the workshop on Friday this week. Okay, so next lecture, it's going to be on Monday. So if you're wondering, when am I going to find the time to do the coursework? Well, we're not going to have the lecture on Thursday and Friday. I'd say that's going to be a great time if you want to think about getting on with the coursework, okay? So you might want to be working on the coursework, other things you might want to be doing. If you haven't done any of the workshop questions, you can work through that. You might want to review the textbook, review some of the lecture recordings. If you want any extra material, with all the lecture recordings, I put extra material in the description for the lecture recording. So it's kind of links in the description kind of thing. So if you're looking for some extra reading, extra questions, anything to read around, all that extra stuff, it's in the description for the lecture recordings. So last important announcement, if you're saying, well, I'm really going to miss having that extra lecture on Thursday, I'd really encourage everyone, especially as we're not going to have the lecture on Thursday or the workshop, we've got a bit of time, come along to the physics seminar on Wednesday afternoon, okay? I'm sure it's going to be an absolutely fantastic seminar, lots of interesting things. So that's Wednesday, 1 p.m, Lecture Theatre 3, and everybody is more than welcome. So I hope everybody has a great week. Hopefully I'll see lots of you on Wednesday. Otherwise, I'll see everybody back here next week, okay? So excellent work with all those questions today. I'll see you guys all next time.